Welcome to this module. So, we are continuing our same lecture and we have divided, like I said, into few modules 2 or 3. First module we have seen the characteristics of op amp in terms of power supply, in terms of the terminals, in terms of the ideal op amp which has infinite input impedance, infinite gain, 0 output impedance, infinite bandwidth, right. And then we have seen the balanced versus unbalanced output and balanced versus unbalanced power supply, also how to apply balanced power supply, how to apply unbalanced supply, and whether the output is taken from the 7 and 4 or between the terminal 6 and ground. If it is between 7 and 4, it is floating. With 6 and ground, then we already know how we are taking the output. Now, in this particular module, what we will see is feedback in op amps, alright, and then further applications also. So, if you come on the screen, what you see is that if you have a op amp and if it is a open loop op amp like this, right, the internal formula of op amp is V out equals to gain into difference of the input terminals. That means that my V out is nothing but difference of this, difference of what? V inverting or non inverting minus V inverting into gain, okay. So, if V plus is greater than V minus, output goes positive, it is correct, right. So, if I have V plus, let us say V plus equals to 2 volts, V minus equals to 1 volt, then what will be my difference? Difference will be 2 minus 1 into gain, that will be 1 into gain. So, it will be positive, correct, it will be positive. But if my V inverting is greater than V non inverting, output goes to negative, right. So, let us now consider that my V non inverting, that is voltage at non inverting terminal is 1 volt, voltage at inverting terminal is 2 volt. In this case, I have 1 minus 2 into gain, that will be minus 1 into gain, that will be minus whatever the output is. So, output is my negative. So, output goes to negative when my V in is greater than V positive. Easy, very easy, right. Now, a gain of 200,000 or 250,000 makes this device practically useless, right, because if it is infinite gain, then how can I use this device? I cannot use this device. That is why the feedback is very important. That is why the feedback is very important, right, because what will I do if I have a gain of very high gain? What will I do if I have a extremely high gain, right? It becomes useless for me. So, to make it useful, we have to apply feedback. Okay. So, one of the feedback is negative feedback, another feedback is positive feedback. So, let us see, infinite gain would be useless except in self regulated negative feedback regime, except in self regulated negative feedback regime. That means, if I apply negative feedback, then I can tweak my gain according to the resistors or the components that I select, and then I can use the operational amplifier in much better capability or capacity. Okay. So, the infinite gain would be useless except in the self regulated negative feedback. So, negative feedback seems to be bad and positive feedback good, right. So, if I give you a negative feedback, you will be unhappy, and if I give you positive feedback, oh, you are excellent student, or somebody tells me I am an excellent teacher, I am very happy. This is our human nature, but in op amp it will not be happy. If you tell op amp, I give you positive feedback, op amp will start oscillating and we cannot control. But if I apply negative feedback, op amp works perfectly, right. So, it is kind of opposite to how we feel. For us, positive feedback is good, negative feedback is not. For op amp, negative feedback is good, positive feedback is okay, we will see the application of positive feedback as well, right. But negative feedback is very important because we can create lot of circuits using negative feedback, right. So, let us see again, come back to the slide. Negative feedback seems bad, positive good, but in electronics positive feedback means runaway or oscillation and negative feedback means stability. stability, alright. So, immaterial of whatever feedback you get, always learn something from that and try to improve, right. So, for the op amp, when you talk about electronics, a positive feedback will cause oscillation or generate oscillations, and negative feedback will lead to stability. Okay. So, imagine hooking the output to the inverting terminal like this, right. This is connected back to the inverting terminal, as you can see here, right. If the output is less than V in, right, it shoots positive. Why? Because this V in is here, right, output is, let us say V in is 2 volts and output gets to 1 volt. So, 1 volt is feedback here. So, the inverting, this is plus, V in is positive here, this is non inverting, this is inverting, that means that 2 minus 1 is 1. So, output will shoot to positive, right. If output is greater than the V in, that means if this voltage I can control, right, this output is there, and if I apply voltage that is 2 volts, then my output will go to positive. Now this becomes let us say, because of my op amp, it becomes 4 volts, then 4 volts will come here, then inverting would be greater than non inverting, right, voltage at inverting will be more than voltage at non inverting, that is why my output will go to negative, my output will go to negative, right, easy, very easy, right, very easy. So, if output is greater than V in, it shoots negative. And results in output, results is that output quickly forces itself to be exactly V in, results is that output quickly forces to be exactly V in, very easy, right. So, now the op amp will do everything it can within its current limitation to drive the output until inverting input reaches V in, correct. A negative feedback makes it self correcting. In this case, op amp drives a current through the load until V in, so that we have here is nothing but a buffer. That means that what it says, that the inverting this way negative feedback, in this case when we apply V in, the output will try to match the input, the output will try to match the input until it reaches the V in, right. And the load a current through the load, the op amp will drive the current through the load resistor, right, until the output reaches its value, which is input voltage V in. That means it is nothing but a voltage follower, is nothing but a voltage follower, right, because whatever voltage I apply, the output will try to maintain the same voltage which is applied at the input, So, this becomes my voltage follower, it follows the voltage at the input, or it is also called buffer, right, it is also called buffer. So, here we have is a buffer, can apply V in to the load without burdening V in with any current, right. Op amp output terminal source sinks at will not like inputs at which will have no current. That means that what we have seen in the golden rules, what we have seen is that the input will draw no current, right. The input of the op amp draws no current, but the output is not like this. Output terminal sources and sinks current at will. Output can source or sink current at will, right. It is not like input that it will not draw current. Alright. So, you have to note this particular sentence. Now, let us see positive feedback. So, instead of negative feedback, which is connecting into inverting terminal, if I connect it to non inverting terminal, in this configuration, if positive input even is a smidge higher than V in, output goes positive. It is correct, right, output goes positive. This makes positive terminal even more positive than V in, making the situation worse. That means that if the inverting input, this one is goes slightly greater than V in, then the output goes positive, okay. And this makes if this gives positive, this makes even more positive at the input, this makes even more positive at the input, because now it is connected to the non inverting terminal, right. So, what we say is that if my voltage at the non inverting terminal is slightly greater than the non inverting terminal, my output will reach to positive, and this positive will again be fed to the non inverting terminal, making it more positive, right. So, this will make the situation worse, the system will immediately rail at the supply voltage, it could rail either direction depending on the initial offset, right, go to the other direction depending on the initial offset. Now, when we see the operational amplifier, according to block diagram of the operational amplifier, it has following blocks. First is the differential amplifier stage, then it has a intermediate state, it has a level shifter stage, and it has a output stage. Okay, 4 basic stages: differential amplifier stage, intermediate state, level shifter stage, and output stage. Now, when we see what is the role of each stage, then we will understand further that how we can use the operational amplifier and what is the role of each stage of the operational amplifier when we talk about the block diagram. So, again coming back on the screen, what we see is that we have 4 stages, and the first stage, input stage or differential stage, can amplify difference between 2 signals, of course, because the differential stage input resistance is very high and draws 0 current from input sources, correct. This is what we have already discussed earlier also, that the stage, the input stage of the operational amplifier would be a stage which will have high input impedance and it will draw no current from the input sources. Intermediate stage used direct coupling, providing extremely high gain. Level shifter stage, this level shifter stage will shift the DC level at the output voltage to 0, right, because we know do not require any output with any DC level. So, DC level would be close to 0, level shifter will shift the DC level to 0, and this can be adjusted manually by additional 2 terminals. By adding 2 terminals we can adjust it manually, we will see. Output stage, a power amplifier stage, has very small output resistance, right. So, the output voltage is same no matter what is the load value, it can be also a voltage follower, it can be also a buffer, So, if you see here, a single op amp will have internal circuit which is shown in the schematic. However, mind it that now most of the op amps they use MOSFET and not BJTs. BJTs are seldomly used, most of the circuit you will find use of MOSFETs. Okay. So, that is very, very important to understand, very important to remember. Now, the essential building block of modern IC is a differential amplifier. It amplifies the difference between 2 signals, has excellent stability, high versatility, immune to noise and interference signal, and hence in most of the analog circuits ranging from DC to high frequency applications, it is used, the differential amplifier is used. Differential amplifier is used in most of the application when we talk about the operational amplifier. All right, easy to understand, very easy, right. Now, let us come to the characteristics of an operational amplifier, op amp characteristics. Okay. So, we have seen this already, that open loop gain, it has voltage gain of op amp when no feedback is applied, right, that is why it is open loop, no feedback is applied, and practically it is several thousands, we have seen that, right, in practical op amp. Input impedance, now input impedance is infinite and typically greater than 1 mega ohm, but using FETs for input stage it can be increased to several mega ohms. You see, when we use field effect transistors, the input impedance will increase to several hundreds of mega ohms. Output impedance, it is typically under few hundred ohms. With the help of negative feedback, it can be reduced to 1 or 2 ohm, very small value. Bandwidth of practical op amp is in open loop configuration is very small, bandwidth is extremely small. By application of negative feedback, it can be increased to the desired value, right. Bandwidth is very small in case of op amp, but if I apply a proper negative feedback, we can increase the bandwidth. Okay, we can increase the bandwidth. Now, let us talk about very important point, which is the input offset voltage. Input offset voltage. So, what is input offset voltage? Let us see. Now, when both the input terminals are grounded, both the input terminals of what? Both the input terminals of op amp. Okay. Both the input terminals of op amps are grounded, ideally the output voltage should be 0. This is correct, right? If I take a operation amplifier and if I say that my inverting and non-inverting terminals both I am grounding, the output voltage should be VO should be 0, correct. This is what I am assuming, because I have grounded this, no voltage at the input, output should be 0. However, in case of practical op amp, a non-zero output voltage is present. So, if you do the similar experiment, what you will see that some output voltage which is in terms of millivolts, you will find at output terminal of the op amp, right. If you write like this 2, 3, 6, 7, 4, right, you will see output at the op amp to be of few millivolts, but not 0, but not 0. So, right, what we are saying, let us see once again, when both the input terminals are grounded, ideally the output voltage should be 0. However, in case of practical op amp, a non-zero output voltage is present. To make the output voltage 0, small voltage in millivolt is required to apply to one of the input terminal. This DC voltage is called the input offset voltage, denoted by VIOS. Very important, very important. So, what we are saying that because the output, when we ground the inverting and non-inverting terminal, because there is some output of millivolts, we have to apply a small voltage at either inverting or non-inverting terminal, to make the output voltage 0. You got it? So, this small voltage that we are applying, this small DC voltage is our input offset voltage, is called input offset voltage, is denoted by VIOS. Okay. All right, good. So, what is the next point? Next is input bias current. Now, what does this mean? We have seen input offset voltage, now it comes input bias current. What is input bias current? So, for an ideal op amp, no current flows into input terminals. We have seen, right, golden rule, no current can flow into the input terminals for an ideal op amp. For practical op amps, the input currents are very small, It is like not no current, you see here it is very small, of order of 10 raised to minus 6 or 10 raised to minus 14, 10 raised to minus 6 to 10 raised to minus 14 ampere, right. Most of the op amps use differential amplifier as the input voltage. The two transistors of the differential amplifier must be biased correctly, but practically it is not possible to get exact matching of those two transistors, correct. So, if I use a differential amplifier, you will see that there is a transistor 1 and there is a transistor 2. Now, this transistor should be biased properly, biased correctly, right. So, but because of the manufacturing, there will be a small change in your beta, between T1 and T2, and due to that you cannot bias the transistor T1 and T2 correctly, and because of which there is a small input current that can flow into the op amp. Thus, the input terminals, which are base terminals of the two transistors, do not conduct small DC current. These small base currents of transistors are nothing but the bias currents, denoted as IB1 and IB2. Let us repeat. I think I made a wrong statement actually. The input terminals which are the base terminals of the two transistors do conduct okay, do conduct small DC current. So, when I apply the when I see that in case of ideal operation amplifier, the input draws no current, right, the input draws no current, we have seen that. But in case of practical op amps, you will see that input draws some amount of current. That small amount of current is because we cannot bias the two transistor at the differential stage, which is my first stage of the operational amplifier. There are two transistors in differential stage, the two transistors I cannot bias correctly. Because I cannot bias correctly, what I see is that the base terminal of the two transistors will conduct some amount of DC current, and this small DC current that it conducts, so transistor 1 is conducting small amount of DC current, transistor 2 is conducting some small amount of DC current. This current is denoted by IB1 and IB2, IB1 and IB2, alright, IB1 and IB2. This is my bias current. This is my, these are small, these are nothing but my bias currents IB1 and IB2. You got it? You got it? Easy, right? Let me repeat once again, okay? Let me repeat once again, because it is very important. Input bias current, input offset voltage, very important. So, now let us see, for ideal op amp, no current flows into input terminals, right, no current flows input terminals. But when you see that in actual op amp, in practical op amp, the current would be small in the sense that there is no current is not correct, it will be 10 raised to minus 6 to 10 raised to minus 14 ampere. Now, why this current flows is because at the first stage of the operational amplifier we are using differential amplifier. When you say differential amplifier, that means you are using two transistors. When you are using two transistors, then we have to bias these two transistors correctly. But practically it is not possible to bias perfectly. Due to this, the base of this transistor will allow or will conduct small DC currents, and this base current we are saying IB1 for transistor 1, IB2 for transistor 2, and this IB1 and IB2 will be your input bias current. This will be your input bias current. Now, we understood, is easy, right, is easy. Let us go to the next slide. Let us go to the next slide. Now, thus the input bias current can be defined as the current flowing into each of the two input terminals. Thus, the input bias current can be defined as the current flowing into each of the two input terminals when they are biased at the same level, when they are biased at the same level, that is when the op amp is balanced. Alright. So, if I have, you can see here, right, if I do this kind of connection, if I connect my circuit as shown in schematic, then my op amp is balanced, but still there is small amount of current flowing into the non inverting and inverting terminal, that is generated by IB1 and IB2, right, and this two bias currents are never same. Hence, average input bias current IB, which can be found by this particular formula, we can find the input bias current. So, what does that mean? What does that mean? That if I have IB1, if I have IB2, right, which is small amount of current present, right, small amount of current present, this is because the bias currents can never be same, right. Hence, how can we find what is the input bias current? We can find input bias current by taking mode of IB1 plus mode of IB2 divided by 2, okay. So, this is how I can find my average input bias current. This is how can I find my average input bias current, alright. Now, let us see one more term, one more term. What we have seen until now? Input offset voltage, then we have seen input bias current. Now, let us see input offset current, input offset current, alright. So, what is it? Input offset current, the difference in magnitudes of IB1 and IB2 is called input offset current. So easy, right. So, in this case IB or input offset current, so I am denoting input offset current by IOS, is nothing but IB1 minus IB2 mode of IB1 minus IB2. Okay. The magnitude of the current is very small, of order of 20 to 60 nanoampere. It is measured under the condition the input voltage of the op amp is 0, right. So, input offset current we can measure when we consider the condition that input voltage to the op amp is 0. So, what we see, input bias current, if we want to find out, the formula is IB equals to mode of IB1 plus IB2 divided by 2. If you want to find input offset current, the formula would be IB equals to IB1 minus IB2, absolute mode of IB1 minus IB2. Okay. Now, let us come back to the screen. If we apply equal DC currents, to the two inputs, output voltage must be 0, right, that is correct, but practically there exists some voltage at the output. To make it 0, the two input currents are made to differ by small amount. This difference is nothing but your input offset current, all right. What does it say? That if I apply equal DC currents to the two inputs, my output should be 0, right, that is correct, but practically there is some voltage at the output, there is always some voltage at the output, you see, ground and output will have some voltage. Okay. So, make this voltage 0, to make this voltage output voltage equal to 0, right. The two input currents are made to differ by small amount. Okay. This current and this current are made to differ by small amount. Thus, difference is nothing but my input offset current. Difference is nothing but input offset. Both input bias and input offset current depends on the temperature. Input offset current and input bias current both depends on what? Temperature, all right. So, that is another thing we have to remember, is that input bias current, input offset current also depends on the temperature, Okay. Now, let us see further an example. So, what is the example? So, if the base currents of the emitter coupled transistors of a differential amplifier are 18 microampere and 22 microampere, that means it is given that IB1 equals to 18 microampere, it is given that IB2 equals to 22 microampere, right. And what we are asked? Determine first input bias current, second input offset current. If I am asked to find this, how can I find this? The two input base currents are given like this, right. Now, I know input bias current. What is the formula? Formula is very simple, IB equals to IB1 plus IB2 mode of IB1 plus IB2 divided by 2. This is equals to 18 plus 22 by 2. This is nothing but 20 microampere. Why? Because everything is micro. Easy? So easy, right? But if I want to measure input offset current, then it becomes even easier, because formula becomes even easier, just subtraction of IB1 and IB2, right. So, what we write? What is IB1? IB1 is 22 microampere, IB1 is 18 microampere. I write IOS equals to IB1 minus IB2, you can see mode, right. This is 18 microampere minus 22 microampere, this will be minus 4 microampere, it is mode. So, answer is 4 microampere, right. This is how we can calculate, what is the input offset current and what is the input bias current, given that you know the values of current flowing to the base of the transistor, all right. This is one example what we have discussed. Let us see one more example, and the example is, how do input bias currents IB1 and IB2 affect the amplifier operation? If this is a question, right, to understand, let us see. To understand the effect of bias current on op amp, let us consider an inverting configuration. So, this is inverting amplifier, Okay. We will discuss this inverting amplifier in the subsequent lectures. Right now you just say that you just see that this is an inverting amplifier. Now if I apply a Kirchhoff voltage law, so I have I1, I have resistor R1, R2, right, and the formula for gain for inverting amplifier is R2 by R1. My gain of inverting amplifier is minus R2 by R1. The current flowing into the from R1 is I1, from R2 is I2, this is IB1, this is IB2, inverting and non-inverting terminals of the operational amplifier. Okay. Now, if I apply Kirchhoff voltage law, what will I have? I1 equal to so I have to go in this particular way, this one, this one, this one, I1 equals to I2, right, I2 plus IB1, right. Applying virtual ground, if I there is another concept called virtual ground, we will see, we will have virtual ground is whatever the whatever my non-inverting terminal, if it is grounded, my inverting terminal is also considered as a ground. Okay. This is virtually ground. Now, we will see about this concept. Right now V minus equals to V plus equals to 0. Therefore, from KVL, Kirchhoff voltage law, and Ohm's law, we know that I1 equals to nothing but I1 equals to V in minus V minus, right, divided by R1. This is nothing but V in by R1, V in by R1, because here V minus, you see, the because of the concept of virtual ground, this terminal will be considered as ground, right. So, V plus equals to V minus equals to 0, right, because V plus is 0 here. So, V minus is also 0. So, if I want to write I1 this particular formula, then how can I find? I1 equals to V in minus V inverting by R1. What is V inverting? V inverting is 0. So, I will have V in by R1. Same way I2 equals to I2, this one, right, V inverting minus V out by R2 is nothing but V out by R2. Right. Now, combining these results, if I combine these results, we have V in by R1 equals to minus V out by R2 plus IB1, right, because we are substituting value of I1 and I2 that we have found here, right. Therefore, the output voltage is V out equals to minus R2 by R1 into V in plus R2 IB1. You see, the output voltage is minus R2 by R1. Now, what I said initially in the starting of this particular problem, that the gain of the amplifier, gain of the inverting amplifier is given by minus R2 by R1. So, V out, if I write, V out is nothing but minus R2 by R1 into V in, okay. So, this we can see here also, minus R2 by R1 into V in, but then there is one more term R2 IB1, you see, there is one more term R2 IB1, and if IB1 is 0, then the results reduces to expected inverting amplifier, right. If I have IB1 equals to 0, then I get this formula, which makes sense, but if it is not, then there is a change, or there is the output voltage has to rely on my IB1, because the IB1 will change the output voltage, rather than it will be minus R2 by R1 into V in, it will be minus R2 by R1 into V in plus R2 IB1. Okay. So, this IB1 into R2 represents your input offset voltage, it represents your input offset voltage, right. It can be analyzed that if the input is not connected, right, Vi equals to 0, ideally V equals to 0, but because of input bias current, if the results in output voltage even when there is no input is applied, right. So, the point is, how can I minimize this output offset voltage, right. So, what we see is that you can see from the output voltage expression that one way to decrease output voltage is by minimizing the feedback resistance R2, but decreasing the feedback resistance, the required gain cannot be achieved. By decreasing the resistance, the feedback resistance, the required gain cannot be achieved, right. So, we have to understand that we have to consider the effect of IB1 only when IB1 is close to 0, then we can have value which is our desired value, alright. So, what we will do is we will stop at this particular point where there is a input bias current, and in the next module we will see further applications or further characteristics of operational amplifier. Till then you all take care, read again once whatever we have seen in this particular module, and the next module we will see how can we understand the other characteristics of operational amplifier, which are the 0 input current, virtual ground. We have just discussed virtual ground concept right over here, right. So, we will see this concept in the next module, so that you can understand further how what is this inverting amplifier, how the virtual ground come into picture. I took an example which is little bit tricky suddenly in middle of this, because you may or may not have idea of how exactly operational amplifier works, or how the inverting amplifier works, or how the virtual ground comes into picture. So, we will see these concepts, okay. We will see this concept. This is just to tell you that input bias current is very important, input offset current is very important, input offset voltage is very important, because this all things we have to use, and we have to make the output voltage balance, that is output voltage should be 0 when our inverting and non-inverting terminals are grounded, then only our op amp is balanced, then we should use it for further applications, right. So, when you design the circuit, you make sure that your output voltage is 0 when your input terminals are grounded. Okay. So, we will see in the next module the further parameters of the op amp. Till then you take care, I will see you in the next module. Bye.